First, let me say why I'm here. And why I'm here is because I would like your advice, basically. Because my background is operations research, as Arvin, am I saying your name correctly? Okay, Arvin said, so I do a lot of stochastic integer programming. I've done some mechanism design. But recently I came across a problem that I thought was interesting in approximation algorithms. So I thought I would work on it. But to be honest, this is like the first work I've done in approximation algorithms. And so I wanted to get some feedback from maybe people who know more about approximation algorithms than I do. So our starting point for this talk is kind of classic results from monotone submodular maximization. So the idea here is I have a set of items, a finite set of items, and I have to choose a subset of them. And I have a limit on how many I can take, so I can only take k. So submodular here, I'm not going to give a formal definition, but basically it means our items, the values are marginally decreasing. So that means that if I have a small set and I add an item to it, it might be worth a lot. But if I have a very big set and I add another item to it, it's not worth as much. Here, we also have a monotone property. So basically, having more items can't be worse than having fewer items. In general, I want more items. And this has many applications, including facility location and sensor placement. And so this problem is known to be NP hard. So we don't expect any polynomial time algorithm. But if you just take a greedy algorithm where you start with an empty set and you go step by step, picking items with the best marginal value, that gives you an approximation algorithm, and it has this approximation ratio 1 minus 1 over k to the k when you're picking k items. A lot of times this is just presented as 1 minus 1 over e approximation ratio, because basically as you increase k, the approximation ratio gets worse, but it converges to 1 minus 1 over e. So at worst, this is a 1 minus 1 over e approximation ratio. And there's a very broad set of literature looking at different extensions of this kind of classic result. So there's work on, different assumptions. In some cases, you can get a stronger approximation ratio, or you look at having constraints, all kinds of things. So the work that I'm going to present follows most directly from basically two papers. One is Golovin and Krauss back in 2011, and one is Ellier et al. From 2021. So Golovin and Krauss is a paper where they define an adaptive version of submodular problems. And so in this problem, our objective function is stochastic. So we don't know exactly what the value of any set of items is. So it depends on the set of items we choose, but it also depends on some randomness. And in this problem, we can choose items one at a time. And then after we choose each item, we observe some information. And presumably this information is somehow correlated with the randomness in the objective, so that as we pick more items, we get a better idea of what our objective is. And we can use that information to make better choices of the next item. Yes.
So when you say the function is stochastic, it's still the function defined over the subsets of the list of items, but the value depends upon some unknown stochastic process. Is that
correct?
So now I have a function over the subsets of the universe, and the value of this function is some expectation over some random process. Is that it?
Yeah, that's a way of thinking of it. Yes.
Will you be showing the definition?
Of which?
of your adaptive submodular problem?
No.
Can you show it on the board perhaps?
Yeah, so basically, one way of thinking about it is you can do, okay, so I can define a function that's basically a function, let's call my set of items. Well, let's just say you can think of it as 0, 1 choice of selecting an item, and I have an item. And then I have this, which is the it's the event space for a probability space. And so then my problem is to choose the subset. So I guess we can, if I'm doing it this way, I can do, so I choose the subsets of items to maximize the expected value of this function. Here omega is some random variable taking values in this space. I guess I'm being a little sloppy here, but I think the better way of thinking about it is actually f is the random variable, but yeah, we're taking an expectation.
So and again, you want X to have a Hamming weight k?
Yeah, and then so something like this. So
Sorry, is the second coordinate independent of the first in F? Is the second parameter independent of the first parameter? What I don't understand is so the model is okay, so there is some random variable distributed on omega, right? And the value of the set S is simply the expectation, right? Now, so we said the expectation of f of S when the second component comes from the random choice.
yeah.
Okay.
So here, well, okay. Here I'm making this actually a collection of random variables. So I guess this is actually here we have f of x. So f of x is now actually going to map to a random variable. That okay. I was a little imprecise at first, but this is better. So f, I choose a set of items, and then that gives me a random variable. They could be any real number. So this is like the most general definition. Most problems have more structure than this, but this is like the most general cases. For each subset, I have a random variable, real valued.
Okay, for every subset, you have a distribution over, right? And you want the subset of size k, whose expected value over its corresponding distribution is maximized or approximately maximized, right?
Yes.
Okay. And how do you access that distribution?
So basically, after I choose each item, I observe a variable, which you can think of. So I observe a variable I'm going to call I, and I can have a variable that's basically it's a variable that's a function of the entire set I've selected so far. So you can think about, I have another collection of variables, one variable for each subset. And each variable, like I of x, is correlated with the variable f of x. And actually, you typically have more structure here too, because I mean, you don't forget information that you've already learned. So
Since there's a theory talk, we want to give the talk on the whiteboard so that because without these definitions, it may be hard to understand, your research.
Yeah, so I didn't really want to give the definitions from Golovin and Krauss because
You
that's
come up
not
with your own
my
definition.
work.
Okay, okay. But when you come to your problem, you'll define it in your.
I was also not going to be very formal in certain parts. I was going to try to be formal where it matters and less formal where it doesn't matter as much. So some parts are less formal and some parts are more formal. But some parts are, yeah. But yeah, I did not really want to go through the whole definitions of Golovin and Krauss because it's not. So maybe we can keep this part informal. So yeah, okay, so but basically the idea is I choose items and I observe information that's correlated to my reward. And to give you a little bit of a more concrete example, suppose we have a social network and we're trying to sell a product and we want to influence as many people as possible to buy our product. So if we give our product to a person, they might influence others to buy the product. So we have a plan where we're going to give away some number of units of our product for free, and we want as many people as possible to buy the product. So at the start, we basically represent this as like as a directed graph, where we don't know whether person one will influence person two to buy the item, but we have estimated the probability. So we can say if I give the item to person one, then there's a 50% chance person two will also buy the item. And we assume that the influence cascades. So if person one buys the item and they influence person two to buy the item, then we also can look and see, okay, person two might influence person four to buy the item, and so on. And here we also assume the edges are independent. So we know the probabilities, but the probability that like knowing that person one influenced person two doesn't tell us anything. It doesn't cause us to update our probabilities anywhere else in the network. So in each step, I pick a person to give the product to, and then I see who got, then what I observe is the set of people that end up buying the product. Here, we don't directly observe the arcs. So we don't observe that person one influenced person two and person two influenced person four. It could have been person one influenced person two and person one influenced person four. We don't know. But we just see, okay, person one, two, and four bought the product. And our goal is just to maximize the number of people who have purchased the product after giving the product to K people. So this is an example in Golovin and Krauss. They give several applications that are kind of similar. You can also think about like, I'm placing sensors, and the sensors, you have some measure about like mutual information across the sensors, but somehow it's kind of random. And then so you place your sensors one at a time and try to maximize the information you collect. Things like that. So, but in the adaptive setting, you choose a policy rather than a set of items. So in classic submodular maximization, we just choose a set. But in Golovin and Krauss, we actually have to choose a function, which is basically if I have a set of items and I have some basically a sigma algebra of revealed information, then my policy is kind of a function of those two things. Yeah, and then our goal is to choose a policy to maximize the expected and objective value. And in this, in Golovin and Krauss, they do provide appropriate generalizations of monotonicity and submodularity. And they show that a greedy policy, again, achieves approximation ratio of 1 minus 1 over k to the k. Something to note is that this kind of looks like an online problem, but actually we are treating it not as an online problem. So we are not when I say approximation ratio, I don't mean a competitive ratio. So here we're trying to maximize the expected value. And so we're trying to find the policy. So when I say the ratio is 1 minus 1 minus 1 over k to the k, I mean that the greedy policy, its expected value is greater than or equal to this ratio times the expected value of the optimal policy. But actually, if I look at specific realizations, the greedy policy could be much worse than an oracle that knows everything in advance. So I just want to make it clear that we are talking about an approximation ratio for maximizing the expected value, and we're not talking about like worst case performance on specific realizations of the randomness. Okay. So more recently, there's been this work, Elliot et al., and they looked at a set of objects they call continuous sequences. And these are a more continuous version of a set of items, and also order matters. So here, a continuous sequence is a sequence of configurations, and each configuration has an associated duration. So here's a little graphic. We could execute configuration A up to time t1, and then switch to a configuration B up to time t2, and then so on. Now, LEA, in their setting, it was non-adaptive, so we're not collecting information. We just pick the whole sequence at once, and then like we get an objective value. We don't learn anything along the way. The objective value is like a function of the entire sequence. So like the order we do things in matters, and each duration matters. And the goal here was to, again, identify the continuous sequence with maximum objective value. And again, you can provide definitions of submodularity and monotonicity. And a greedy algorithm provides an approximation ratio of 1 minus 1 over e this time. And this time, this is like, you don't have this k thing. You actually have a continuous setting, so your approximation ratio is 1 minus 1 over e. So these are kind of the two works that I'm kind of building off of. Oh, yes. So LEA also defined things called discrete sequences, which are just sequences of configurations. And again, the objective value depends on the entire sequence, with ordering matters, but still non-adaptive. And their goal is to identify the discrete sequence with maximum objective value. And again, you can define submodularity, you can define monotonicity, and you can get an approximation ratio of 1 minus 1 over k to the k. Something to note is that their proofs for the continuous sequence and discrete sequence are just completely separate. There's no overlap, like no lemmas used jointly between them or anything. They're just completely separate. They have some similarities in terms of like the strategy, but they treat them just as two separate problems that they made two different proofs for. But if you think about these results, they seem like they should be connected. Like all of these results involve submodularity, they involve monotonicity, they all produce basically the same approximation ratio. And okay, there are some connections that are fairly straightforward. So discrete sequences are a direct generalization of the classic setting, or you have a more general class of functions because the order of the items can matter. Instead of the classic setting, order of items does not matter. And the adaptive setting, Golovin and Krauss, directly generalizes the classic setting. You could just like forget the information. Like you could say every step, I don't collect any information, and then you're kind of back to the classic setting. And it's probably not too hard to combine discrete sequences with the adaptive Golovin and Krauss setting in order to develop a theory of like adaptive discrete sequences. So all of the discrete settings seem like you could connect them pretty, like not too much difficulty. But the really different thing is the continuous sequences. So how do continuous sequences fit into all this? Because there's really pretty big differences between continuous sequences and the other settings, at least at first. Because, okay, all the discrete settings are discrete, you have a finite set of options, but in continuous sequences, you actually have a continuous set of options because the durations can be, any real number. So the objective function for continuous sequences, they also require that to have a type of differentiability property. Basically, if you fix a sequence and you look at how the objective changes like over time from the beginning to the end, that has to be differentiable. But when we were looking at the discrete setting, I mean, there's no derivatives in that setting. And when you look at how they prove results for continuous sequences, they basically bound things by coming up with inequalities or differential inequalities, actually. This says differential equations, but they're actual differential inequalities. And that's how you get your approximation ratio. But the other settings are discrete, and they're analyzed basically using combinatorial techniques. So how would we unify these approaches? So we define a problem we call the adaptive switching problem. And it's going to generalize all of these settings. And we are going to define submodularity and monotonicity for this problem. And we are going to prove that a greedy policy achieves an approximation ratio. And the approximation ratio is a little bit complicated, but it does recover the existing ratios. So in the discrete setting, you do actually get 1 minus 1 over k to the k. And in the continuous setting, you get 1 minus 1 over e. So that's what we're going to do. So how do we define the adaptive switching problem? Well, it's somewhat similar to the continuous sequence problem where we have a finite set of configurations. And we decide when we're going to change configurations, and we choose what configuration we're going to choose to. But there's two major differences. So one is we are going to make it adaptive. So we are going to bring in elements from Golubev and Krauss, where we're collecting information depending on the active configuration. And the second thing is that we're only going to be allowed to change configurations at specific points in time, which we call the time scale. So we denote the time scale with this with t, and we allow it to be any closed subset of the interval 0 to infinity. So if we set t equal to the natural numbers, then configurations are chosen in discrete stages, and we get like a discrete setting. If t is equal to the interval from 0 to infinity, then we're constantly choosing which configuration we want to change to. And more general settings are possible. You could really go crazy if you wanted. So one example here is we take a bunch of unions of continuous intervals. So you have some continuous segments, and then you have some discrete jumps. You could actually just like glue a bunch of Cantor sets together if you really wanted to get wild with it. But any closed subset is fine. So a switching path now is going to describe a sequence of configurations with association durations, but we have an added restriction that the configuration can only switch at points of the timescale. So here's an example of a switching path. Here the time scale is like a union of intervals. And so if we're at an interval, we can switch at any point within that interval, but I can't switch at any of the times here that are not in my time scale. So I'm stuck here, I would be stuck with configuration B until I reach this point. Yeah, and can only, and we do require that the configuration can only change a finite number of times within a finite within any finite interval. So basically, mostly to avoid like really irregular stuff. Yeah. So this is a generalization of discrete typo there. This is a generalization of continuous sequences, and it's a generalization of discrete sequences. You can see that if you set the time scale to 0 to infinity, you get continuous sequences. If you set the time scale to the natural numbers, you get a discrete sequence. And then we're going to let, so if I have a switching path A, I'm going to use this kind of like cardinality notation to denote its length. So if a switching path describes something up to some time t, cardinality of A equals t. Okay, so here maybe I should have been a little bit more, I should have given the formalizations here, but I can give them now.
Actually, just going back, in the adaptive switching problem, could you just throw some light on what is being optimized?
Yeah, so
The value of the configurations added up.
well, it depends problem to problem. I could skip ahead and show you an example. Well, one example actually.
So it's some submodular function of the selected configurations, is that right? Or-
Yes, so it depends on the whole thing.
Okay.
So if I change any of the durations, it might affect my objective value. If I rearrange things, that will. Yeah. And actually, one example that we've already seen is viral marketing, because the discrete setting is a special case of this. And so that's one example. I'll show another example in a little bit. So basically the way I formalize this is similar to what I did here. So we can think about there being a collection of variables indexed, basically a collection of variables indexed on the set of possible switching paths, which is uncountable, but yeah. So we again have a function that, so for each switching path, we have a variable. It's the objective value. We also have, so our goal is to maximize over paths in switching paths such that the cardinality is less than or equal to k. The expected value of this variable. In terms of information collection, we do collect information as we go on. It's random and it depends on the entire switching path. So the way I formalize this is I define we assume there's what's called the information collection function, which is a function of the current configuration and the switching path up to that point. So again, this is going to be a collection of variables. So for each configuration and for each switching path, we get a variable. Actually, it might not be real value, but I have some space of possible information I can collect. And then basically I can look at my switching path and I can define a restriction up to a specific time. So this means follow the switching path, but instead of following it to the end, stop at time t. And I can kind of gather all these variables together. And so I can kind of define a stochastic process that depends on my switching path, that just strings all of these together. So it's just, I look at the information for the configuration that's active at time t of my switching path and my switching path up to time. So that's how I formalize information collection. And presumably this information is correlated with the objective value variables. Otherwise, there's no point in collecting it. Okay, so that's the objective function, information collection. And then a policy is a function that basically it takes a switching path, and we can call this like an information path. So basically a path in this stochastic process. So it takes a switching path and what we might call an information path, and it produces a configuration. So it says, if I did this switching path and collected this information path, then I'm going to give you the configuration that you should switch to immediately after executing this switching path. So our goal overall is here. This is actually a little sloppy because we're not actually choosing a single path. What we are going to end up choosing is a policy. So yeah, we are going to choose actually max pi in the set of policies, and we want to maximize the expected value. And then it's convenient to have this capital F of a policy is just the accumulated rewards up to a given time. Actually, the expected accumulated rewards. So F has the expectation built in. And this will be up to some time n. So, yeah. Any questions on that setup? Okay, so yeah, so one example is viral marketing, which we've already talked about. Another example, this example is something that LEA et al. Were working on, except here is an adaptive version. So if you type something into Google, you will be shown ads. So for any keyword you search, the way it works is there are advertisers that will pay the search engine to show the ads. And these are usually tied to a keyword. So if you search, I don't know, cats or something, then, or cat food or something, then you have people, advertisers who have bid on the keyword cat food. And then Google has a choice of which ads am I going to show and in what order am I going to show them. So here we assume users arrive via a Poisson process. And if a user clicks on an ad, then they pay the search engine a certain amount, which is typically previously negotiated. And the advertisers also are able to specify a budget. Basically, they say, okay, I'll pay, I don't know, a half a cent per ad. But I'm only going to pay for the first 10,000 clicks. After that, you can stop showing my ad. Here in this problem, we're going to assume that you can keep showing the ad after the budget has run out, but you stop collecting revenue. And these ads, typically these days ads are personalized, I guess, but for simplicity, we are not going to treat these as personalized, but you can change the configuration over time.
What's the configuration here?
So the configuration is what ads am I showing in what order? So potentially you could have a
list of ads that are shown.
Yeah.
What is the time duration? What is the time interval that's going to change? The time scale?
So the time scale here for this problem will just be 0 to infinity. And the point is I can change the ad configuration at any point in time. So just time goes forward, users come in, and then I show them each user that comes in, I show it some ads, and they click on the ad or they don't click on any ads. and it progresses that way. And my goal is to maximize my expected revenue. So yeah, and the main reason I changed my well, yeah, so you can change your configuration at any point in time based on the information you've seen. One big reason is if an ad runs out of budget, then you would probably stop showing it in your ads. But there are other things. For example, if at first you thought an ad was going to like run out of budget very quickly, then you might focus on other ads, I guess. But if people don't click on that ad as much, you might bump it up, something like that.
And the randomness comes because of the Poisson process.
And there's randomness in terms of whether a user clicks on an ad or not.
Do you assume you know that the preference distribution?
Yeah, so we assume that for any given configuration, I can at least estimate reasonably well what the probability is that a user will click on each ad. Here, I'm not focusing on it, but you don't have to be perfect. But if you can estimate it within a ratio, you can still get an approximation ratio, although it will be worse than 1 minus 1 over t. But here, let's just assume I know the probabilities exactly. So,
if it's the same Alai, he was a PhD student here.
okay.
His name is Saeed Alai. I think the name is pronounced Alai. And even during his PhD, he did some work on advertising kind of stuff. He was a student in our department. Yeah, he probably still is at home.
I think, yeah, I think that's him. But I think he would have been a student a long time ago.
Graduated maybe in 2010.
But yeah, I think that's him. I'm not 100% sure. I haven't met him. I met one of the co-authors. So this paper came to my attention because so there's a guy at Duke called Makdumi.
What? Sumi?
Makdumi is his last name. I'm kind of blanking on his first name right now. But he came and talked when I was at Minnesota. And that's how I became aware of this work. But yeah, I don't know Alahi, but it would make sense for what you say to be true. Okay, so this is an adaptive switching problem on the continuous timescale 0 to infinity, where my configurations are the set of possible configurations of ads. So what ads and in what order. And then my switching path here basically tells me which ads were I showing in what order at different points in time. And then the information that I collect is I get to see when a customer arrives, which is to say I get to see when somebody searches something, and then I get to see whether they click on any ads or whether they don't click on any ads. And if they click on any ads, what ads did they click on? And my goal is to maximize total revenue. Okay, so here I mentioned that we can have more complicated timescales or less conventional timescales, like a union of a bunch of intervals. And to be honest, at the moment, I don't have any convincing applications. And there's actually reasons why I don't have any convincing applications that I will talk about later. 15 minutes.
So when you talked about displaying ads, you were trying to maximize revenue from one single user, right? I mean, it's not
maximize revenue over a period of time.
over a period of time.
Yeah, so you fix a period of time, say a quarter or a week, and you try to find the policy of switching ad configurations at the right time to maximize your revenues. Okay, so our existing, like all of the settings I talked about prior to this setting, they require monotonicity and they require submodularity. So how are these concepts defined in this setting? So we don't actually exactly do monotonicity. So I define a new property called boundedness. And I'm not attached to this name too much. So if you have a better name for this property other than boundedness, feel free to share. But basically the idea is, suppose I have some policy called pi that I execute up to some time t. Now, I could have instead executed a different policy pi prime up to some other time t prime. Now, basically, the idea of boundedness is I want to make sure that I can never like dig myself into a hole that I can't get out of. So the idea is after executing pi, I should be able to switch to another policy. And I should be able to eventually reach the same rewards that I would have gotten if I had just done pi prime up to time t prime. And in addition, the amount of time it takes me to get to that level of reward can't be too much bigger than t prime.
So if you concatenate pi prime itself instead of c, would it not give you what you want?
In some settings, yes. In other settings, you cannot do that. So in fact, that's a nice segue to the next slide. So in the continuous sequence setting, in the like if my time scale is 0 to infinity, typically you can concatenate pi prime and you get, so here actually, before I move to that, so we'll call a problem beta bounded if depending on the extra amount of time that's required. So if it takes me t prime plus beta units to get to this objective, it's beta bounded. So in the continuous sequence setting, it's 0 bounded. I can just execute pi prime for t prime time units. And if you look at the existing works, and if you apply like similar kinds of assumptions, like the type of monotonicity that's there, this will be 0 bounded. And same with discrete sequences or discrete setting. However, the problem if you're doing it on a general timescale is that because I can't change configurations whenever I want, I can't necessarily just concatenate a policy. So for example, if I have a continuous time interval and then a discrete jump, then this policy pi prime could be changing things continuously, but here I have to stick to one configuration. However, what I can do for this specific time scale, that's a bunch of intervals glued together. And these intervals are all the same width with the same gaps in between them. Actually, the most important thing is, no, they do need to be the same width. So same width and same gaps between the intervals. Then what I can do is I can just wait until the next interval starts. And I can do whatever I want up till then and then execute the new policy. So you can get a beta bound that way. So this is why I define beta boundedness. This way we still can get results on mixed timescales. Questions about that? Okay, so how do we define submodularity? So we require marginal values of configurations to be non-increasing. But how do we define marginal values in this setting? So if I'm thinking about a discrete setting, the marginal value is basically a difference. It's the difference between my value once I've added the item minus the value without the item. In continuous settings, the marginal value is a derivative. It's rate of change of my objective when this configuration is active. If I have a mixed setting, then the marginal value could be either a difference or a derivative. And so the central question is, how do we unify the discrete time setting with continuous time setting? And actually, there is a field of work in the area of dynamic systems that actually looks at this question. So you can define a difference equation or a differential equation. So you can define a differential equation. Here's an example of a simple linear one, where you say my derivative is some function of my current state. Or you could define like difference equations where I can say, my function in the next time step minus my function now is some expression in my current function. But there has been work that combined these two things on an arbitrary timescale. And so I'm pulling a definition that already exists. I didn't come up with the idea of a delta derivative, but it has been used in these dynamic systems on general timescales. So in order to define this, we first define a forward jump operator. And that's basically just the point after this point. And if I'm in a continuous time interval, then it's just the same point. So here, if I have these intervals glued together, the forward jump operator for 0.5 would be 1, but the forward jump operator of 1 would just be 1, and the forward jump operator of a quarter would just be a quarter. And then if I have a function that's real valued on a general timescale, I can define its derivative. Typically, people working in dynamic systems on timescales, they don't like to do cases like this. They like to provide one definition that handles both cases. But actually, the definition of a delta derivative, it's equivalent to, you can break it into cases. And so if my forward jumper operator is the same point, so then I'm kind of in a continuous interval, then basically I get something that's like my standard derivative, where I take the limit of the ratio of the difference in the function divided by the width of the interval. Here, to define this limit, you just look at points in the timescale. So this is the limit as s approaches t, where s is a point in the timescale. If my forward jump operator is bigger than my point, so I'm doing a discrete jump, then I define it to be just basically a difference. So this is like your standard slope calculation. And here it's shown kind of graphically. So if I'm in a continuous region, I kind of take, a tangent line. And if I have a discrete jump, I take the slope across that jump. Okay, so we are going to use this delta derivative to define marginal values. So suppose I execute some switching path up to some time cardinality of A, and then I switch to a configuration C. So what I can do is I can define a function that's a function of the information I've collected along my switching path A. So this is actually a random variable depending on the information I've collected. And then I can define it from the end of the switching path forward. And I just define it to be the conditional expected accumulated rewards, given the information that I've collected at this point of time, if I stick to configuration C from here forward. So I say, I'm going to switch to configuration C. I'm just going to stay in configuration C for the rest of eternity. And this function gives me what are my accumulated rewards going to look like given the information that I've collected. And then I define my marginal value to be the delta derivative of this function, basically just at the beginning of where this function is defined. So that's how I define a marginal value. Any questions about that? Okay, so now that we have a marginal value, we can define submodularity. So basically, I'm going to say that a switching path B extends another one A if it's longer and they agree up to the shorter one. So here we have switching path A, and switching path B does the same thing until the switching path A ends, and then it does whatever. And then to be submodular, I say that the marginal value of a configuration given some switching path has to be greater than or equal to the marginal value of the same configuration given a longer switching path. Question? Okay, so the definitions that I've given, they do generalize the existing definitions, so you can show that, you know, in the specialized case, like on the time interval 0 to infinity, using the same assumptions that alloy use, then yeah, the definitions agree, and same with Golovin and Krauss. Oh, something I should have mentioned with boundedness also. So boundedness is kind of a weaker restriction than monotonicity. So these settings also satisfy boundedness. If you're monotonic, typically you have this bounded property. Yeah. So, and these two problems I talked about are submodular, and they are, actually both of these are zero bounded. So one thing I want to point out is that some things that you might think intuitively as being marginally non-increasing, it turns out on a mixed timescale, they might not be. And an example here is, suppose I have this add configuration problem, but I have to stick with whatever add configuration I choose at the beginning up until some specific time t, and then I'm allowed to change. So this might actually not be submodular, because if I think about two add configurations that don't share any adds, I can think about some switching path I can think about the empty switching path, so I haven't done anything yet. And I can think about the switching path where I just execute A up until I'm allowed to change. And if I compare the marginal value when I haven't done anything with the marginal value of when I've already executed A, the one where I've executed A might actually be bigger. And the reason is this here is an instantaneous rate of change. And this change here is like an average over the whole interval. So if I'm executing this add configuration over this whole interval, you know, my ads will start to run out of budget and my revenues will decrease. And so I'll actually get a lower slope than if I were to do something else and then get this instantaneous rate of change. So we have a situation where, okay, this problem looks marginally non-increasing, and it is in the timescale 0 to infinity, but it's not marginally it's not submodular in the timescale 0 union t to infinity. And to be honest, like I haven't found, it seems pretty hard to come up with something reasonable that's not like trivial that stays submodular. So this is an issue I've been having that I was hoping maybe I could get some advice on, but it seems
I
like.
can tell you a very good person to get advice on. That's Nate. He's my student who's been working on submodularity for a long time. Nate, why don't you talk to Alex after? Sure.
Okay, yeah, that would be great. So I mean that, yeah, because I've kind of tried to come up with things, but it seems, okay, so you can make everything just linear where you don't have any marginal non-decreasingness at all, and that works. That will be submodular according to this definition, but it's also trivial. So like you just pick the thing with the best rate of change because your rate of change never changes. So, okay, so I haven't found a good way to get around to this problem. So I don't really have it. This is why I don't have any convincing applications in the mixed timescale setting, is because it seems pretty hard to have something non-trivial that's still submodular in a mixed timescale setting. Okay, so it's already 3:30. Is it okay if I go a few? Okay. So let's talk about our approximation ratio. So in the discrete setting, we had this approximation ratio. And it turns out that this comes up because you run into expressions that look like this difference equation. And this is actually the solution to this difference equation. I mean, actually, the things that come up are inequalities, but then that gives you a bound based on this. And in the continuous sequence setting, you get an inequality that looks like this differential equation. And the solution to this differential equation is e to the negative t over k. And so you get an approximation ratio that ends up being like 1 minus 1 over e. So we can show in our setting, you still have a greedy policy that selects the configurations with the highest marginal value, and that achieves an approximation ratio. But the question is, what is the approximation ratio? So it turns out there's already an established notion of an exponential on mixed timescales, which is just, I define it to be the solution to this delta derivative dynamic equation. So E gamma t is the of t is a function that's the unique solution to G delta of t equals gamma G of t with G of 0 equals. And this does have some properties analogous to the standard exponential. And special cases, E gamma of t on the just natural numbers is 1 plus gamma to the t. And on the continuous interval, it's e to the gamma. Here on the right hand side, e is the usual, that's the usual e to the gamma. So what we actually end up showing is that our greedy policy achieves an approximation of e negative 1 over k applied to the value k. Sorry, 1 minus e minus 1 over k of k. And so if you go back to here and you plug in like negative 1 over k for gamma, and if you plug in k for t, you get, this does recover the approximation ratios we had in the previous.
This is independent of beta, the value of beta?
Sorry, this is the case of zero bounded. For beta bounded, it's negative 1 over beta plus k. Sorry, I don't remember what the expression is, but yeah, so zero bounded, this is the expression for zero bounded. In beta bounded, it does depend on beta, but as k gets large, the beta term doesn't matter.
So it's probably beta plus k in the denominators.
Yeah, that's what I think. I think it should be minus 1 over beta plus k in the denominator. Yeah, on a small time scale, the beta can have a big influence, but the influence of beta goes to 0 as k goes to infinity. So if you have a large time scale relative to the beta is not important. And in terms of our proof, well, I'm obviously not going to provide a proof now, but we use techniques from dynamic equations on timescales. So we basically come up with an inequality that kind of resembles this, and then you can show that you basically have existing results that show that you can then bound that by this exponential. So our proof kind of combines similar strategies to what all of the existing works do in terms of setting up a dynamic equation that has this certain factor bound. And then we use techniques from the dynamic systems on timescale, actually just a resulting theorem from there to show that we get that approximation. Okay. So that is my talk.
So thanks a lot. We hope to have more interaction with you. So so I asked Nate to talk to you, and maybe you and your students. Yeah. Any other questions?